Morning, everyone. My name is Zhang. I'm from Xi'an Jiaotong University from China, and I'm currently a visiting student at UNC Charlotte. And today I'm going to talk about the work I've been doing. It's called Learning Multi-Layer Coarse-to-Fine Representations for over 10,000 image categories. So I'll introduce our work in these four aspects. First, I go with the introduction, related work. Although in recent years the problem of image classification seems to be well studied, since the state-of-the-art methods have reached impressive accuracy rates on classifying 1,000 or fewer image categories. However, recognition thousands or even tens of thousands of image categories is a still challenging issue, as the number of categories is much bigger and the accuracy rates for current methods are much lower. Besides, computational costs at testing phase grow significantly as the number of categories grows. So, however, when the number of categories gets bigger, there are more information that we could exploit. Some image categories may come from different semantic levels. For example, the concept of dog and husky. Husky is a kind of dog, and so these two concepts they overlap. That is, they are not mutually exclusive, and there are also visual correlations between different categories. Like the animal donkey and horse. They are different species, but they look alike. So they have visual correlations between them. And there are also semantic correlations between different categories. The same example, like dog and husky, in the concept ontology, the dog is a parent node of the husky. And something like that. So the question is how to leverage these correlations to organize tens of thousands or even more numbers of categories for classification. So in the field of large-scale visual recognition, tree structures are widely used to hierarchically organize large numbers of image categories. Such tree structures can be categorized into three types. So these methods are just there are three types. First is hierarchical tree of binary classifiers. The second is semantic ontology, and third is label tree or visual hierarchy. And these methods all just leverage one kind of correlations, either visual or semantic. So in our work, we try to solve the problem from different aspects using both visual correlations and semantic correlations. So the contributions of our work are as follows. The first is deep network is used to learn more discriminative features for over 10,000 image categories, which are not atomic or mutually exclusive in the semantic space. And second is visual semantic trees learned layer-wise with constraints generated from semantic ontology. And third one is we integrate our visual semantic tree structure with Xi'ans for large-scale image categorization. And here is some more detailed introduction of our work. There are three major parts. The first is visual semantic tree construction. Second is classifier training over VS tree, that is visual semantic tree. And the last part is integrated method. Goes with the first one. As it has been proven that the decaf framework has good generalization ability for image classification tasks on different datasets, so we simply apply the decaf model for feature extraction on the ImageNet 10K dataset. According to concept ontology for the 10K categories in WordNet, there are 7,756 atomic categories and 2,428 non-atomic categories. Images of non-atomic categories may come from its descendant categories, which means that some images of the same category, same object, may have different labels. The regular Xi'an network just ignore this kind of relations, so it's not the optimal way to handle the problem. So in order not to confuse the computer, so we just adapt the decaf framework to 7,756 outputs and fine-tune the decaf model with images from 7,756 atomic categories. And we extract 4,096 dimensional outputs of layer fully connected, seventh fully connected layer as visual feature vectors for all the images, including both atomic and high level. Then we use the extracted deep features to estimate inter-category visual similarities for 10K image categories. Firstly, as images in a high-level category actually come from multiple descendant atomic categories. So we assign each one of the images in high-level categories to nearest atomic category in visual space. The images from high-level categories are then relabeled by the atomic categories they are assigned to. And then we estimate visual similarities among different atomic image categories. To estimate the visual similarities between different image categories, we need to find a way to describe the overall visual properties of each category. Considering the intra-class diversity within each image category, we cluster each category into 30 groups, and the category is represented with the 30 group centers like below. After we got the description of the image category, we can calculate inter-category visual similarities between different image categories. The symmetric visual similarity matrix for 7,756 image categories is denoted as AV, like below. Each element Aij of matrix AV shows the visual similarity between category I and category J. Another aspect of correlations between different image categories is semantic correlation. We use this kind of correlation to generate semantic constraints for the process of tree construction. According to the concept ontology we built using WordNet, we define a number of edges in the shortest route from one category to the other as the semantic distance. And similarly as in visual space, the semantic distance matrix is denoted as AS. Then we apply clustering method on image categories to generate clusters according to the matrix AS. Semantic constraints, musclings, and canal links are generated according to the clustering results and the parameters, the two parameters lambda m, lambda c. Here is an illustration of generation of semantic constraints. In this graph, there are totally 15 image categories in the concept ontology. 8 of them are atomic categories, which are labeled with digits from 1 to 8, while the others are high-level categories. The 8 atomic image categories are clustered into 3 groups, which are marked out with rectangles in different colors, according to their pairwise semantic distance in the ontology. We have musclings between categories of the same groups and cannot link between categories from different groups. And the two parameters are shows the percentage of the total number of musclings or canal links we should use to affect the process of a tree construction. For example, in this graph, originally there are mass links between the category 1 and 2, 3 and 4, 5 and 6, 7 and 8, and so on. But when we have the parameters lambda m equals 0.2 and lambda c equals 0.5, the only mass link left is the one between category 7 and category 8, and similar with canal links. For large numbers of atomic image categories, the intercategory visual correlations matrix AV can be used as a proxy to determine their intercategory separability. The visual similar atomic image categories are more difficult to be separated, thus they should be assigned into the same group to avoid early incorrect partitioning at a high level node of the visual semantic tree. At the same time, we use semantic constraints, that is mass links and canal links, as side information to adjust each splitting step of the tree construction. We collect semantic constraints for all the atomic image categories, atomic image category pairs, and represent them as a constraint matrix Q. And then we integrate matrix AV and Q and apply the flexible constraint spectral clustering algorithm for tree construction for each layer. And this inequality here controls how well the semantic constraints are satisfied, which decides whether the tree construction is affected more by visual correlations or semantic correlations. The partitioning process is applied in a top-down fashion, recursively from the root nodes in the first layer to the leaf nodes in the last layer. And each leaf node contains one single atomic image category, or the tree reaches the maximum depth. The fine-grained atomic image category, which shares significant common visual properties but contains subtle visual differences, are finally assigned into several sibling leaf nodes under the same parent node. During the process of tree construction at different non-leaf tree nodes, we leverage hierarchical semantic constraints generated from different scales in the concept ontology for tree node splitting, and the specific scale in concept ontology are denoted by the atomic image categories that are associated with the current non-leaf tree node. Here are some example views of our visual semantic tree. The image categories at sibling leaf nodes are both visual similar and semantic similar. Here are some more. Okay. After the visual semantic tree is constructed, we train multitask SVM classifier hierarchically over it. Because it's a hierarchical structure, between adjacent layers, we add a constraint to enforce that the training instance should first be able to be assigned into the parent node correct, if it can be further assigned into the child node. And we propose another integrated framework for large-scale visual recognition. We integrate decaf model with tree structures to learn hierarchical classifiers. And we put categories to different groups according to the tree structure and train neural network for each group. And third, we train a tree classifier for the root node. And here's the illustration of the integrated framework. We fine-tune the decaf model using our dataset and extract features for each image. Then we construct a visual semantic tree and use the first layer of the tree to partition all image categories into B groups. After that, we fix the weights of the first 5 layers of the network and specifically fine-tune each copy of the rest layers. So in the testing phase, each test image first is divided into one of the B groups and then goes down through the 3 specific layers in that group. So this experiments. We assign the image of 2,428 non-atomic categories to 7,756 atomic categories and relabel them with low-level labels. And we use the data in a two-fold fashion, half for training and half for testing. And there are 4 parameters should be preset. That is B, H, lambda M, lambda C, and H is for the maximum depth of the tree structure, and B is for number of splits that each non-leaf node should be splitted. And lambda M is for the ratio of musclings that should be used as semantic constraints, and lambda C is for the ratio of canal lengths. And we perform comparisons on different methods in terms of average top 1 classification accuracy for all the categories and the computational cost for one test image during testing phase. And here is suppose it takes one dot production operation to calculate the score for one image category. As we use the same visual features in different methods, it's reasonable that we evaluate the computational cost at testing phase by calculating the average number of dot production operations needed for predicting one test image. We construct both label tree and visual tree with 3 different configurations. As shown in the table, our visual semantic tree, that's VS tree method, can reach the best classification performance among all the tree methods while having very competitive computational efficiency at testing phase. And we also compare the average top 1 classification accuracy and computational cost at testing time for different deep networks. We compare with our integrated framework. We also build a similar integrated framework. Well, the only difference is that the 7,756 atomic image categories at the root node of the tree structure are randomly and evenly partitioned into 10 groups, rather than following the guidance of a semantic visual tree. The average classification accuracy for the network integrated with VS tree is higher than the accuracy for the network with random partitions, and the flat decaf model, which proves the way in which our visual semantic tree organizes image categories, can effectively improve the classification performance for large-scale image categories. And for each network structure, we sort the image categories in ascending order in terms of classification accuracy. In this graph, it's demonstrated that our integrated model has higher classification accuracy for most of the categories. In addition, the classification accuracy of our VS tree method with hierarchically multitask SVM classifiers, which is 11.64% for configuration B10-ish for M25C5, is very compatible with the accuracy of the flat decaf model. The computational cost for our method is only 0.5% of the cost of the flat decaf model. At last is the conclusion of our work. First is a deep network is used to learn more descriptive features for over 10,000 image categories, which are not atomic or mutually exclusive in the semantic space. And second, visual semantic tree is learned layer-wise with constraints generated from semantic ontology. And last, we integrate our visual semantic tree structure with CNNs for large-scale image categorization. Oh, that's all. Thank you.
From your result graphs. Some of the categories are very well classified, about some hundred, and 30,000 categories are the classification across are very low, right?
Yeah.
So could you give some examples, well classified category and bad classified categories? Some examples.
Can you repeat your question? The last sentence, I didn't catch that.
Could you give me some examples of well classified categories and badly classified categories?
Oh, okay. Maybe some very fine-grained categories, they are very difficult to classify. So these categories may have very low accuracy rate, while the others that may be more easier and they are more separable, so they have higher accuracy rates. I don't really have the figures here, so I can't really show you that. But that makes sense. Just the categories that are more visually similar and semantically similar, they are harder to classify. So that's it.
Thank you very much.
Thanks.